Good. So we are going to start this colloquium today. So today's speaker is Professor Olga Fink. She has a chair in Intelligent Maintenance Systems at the ETH in Zurich. And her areas of expertise, among others, are in deep learning, decision support algorithms, and diagnostic and prognostics of complex industrial assets. Her presentation will be about domain adaptation and hybrid algorithms for intelligent maintenance systems. So without further to say, Professor Fink, the floor is yours.
Thank you very much for the invitation, but also thank you very much for everyone for attending and your interest in the topic. And if there is any question in between, please feel free to interrupt me and I will be happy to explain additional details. So we saw recently, but also already for a while, quite some impressive results of artificial intelligence in many different domains, and among others, this was in the field of detecting breast cancer in images where AI algorithms were outperforming domain experts. But typically what this algorithm do require is massive amounts of data, and on the example of ImageNet where everything was actually labeled. And this is also one of the limitations, that typically they do not only require data, but also for each of the samples they require also labels, so they need to know what there is to learn, so they need some supervision. And actually, it looks like it's a very promising approach also for monitoring complex industrial systems, since they do typically collect quite some data, and they are typically nowadays also heavily monitored. But if we go back to the requirements of when we can really apply deep learning and machine learning, it's when we also have quite some data, and typically faults are rare. And in terms of learning faults, this will be our labels. And since faults are rare, we typically do not have labels at all, or partly we would have just some few labels to learn from. When we take a new system, so then the situation can be even more difficult, because in this case we do not only have lack of labels, but typically we also have variability of operating conditions, and it may take some time really to cover all the operating conditions so that we have a representative data set for us to learn from. And what we do require are interpretable, scalable, and generalizable algorithms if we are to apply them in the context of complex industrial systems. And if we take the case of machine learning algorithms, they are typically black box models. So how do we overcome this, and how do we come to this interpretability, scalability, and generalizability when we deal with data and when we deal with complex industrial systems? So what I wanted to cover in my talk are actually two topics, and one topic is a bit subdivided. So on the one hand, I wanted to show some examples of how domain adaptation can be used to leverage some of the challenges that I just outlined. And on the other hand, I also wanted to discuss with you how combining physical performance models with deep learning algorithm could also help to overcome these challenges and to make the algorithms really scalable, generalizable, and interpretable. So since I wanted to discuss these two topics, and not just domain adaptation, but also unsupervised transfer learning, I just wanted to show to you quickly in which field we actually are and how we are distinguishing these two fields. So the first case study that I will be showing you is in the field of domain adaptation. And what we need in this domain adaptation area is we're actually trying to use information from something where we know more about and to transfer it to something where we know less about. So we have a trained model, and we try to use it either for different tasks, or we try to use it for the same task but for a different domain. And in the case of unsupervised domain adaptation, we do have labels for our training data set, But for our testing data set and for the target data set, we actually don't have any labels at all. So this is the case of the unsupervised domain adaptation. And the more challenging task is if even in the source data set we don't have any labels at all. So we do try to learn from that, but still we don't have any labels. So this is the second case, and in fact this is even a more challenging case. But I will walk you through, so just to show you the distinguishment already at the beginning. So the challenge that we're trying to tackle in this case is to improve the scalability into generalizability. And the setup that we are starting with is that we do have some faults available during training, and we would like to adapt the models that we trained on some other conditions toward a new domain. And obviously, if we are able to do that, we don't have to train the models for each of our different operating conditions. And we can start using them, but still adapting them to the specific operating conditions and specific environmental conditions. So the first case study that I wanted to discuss with you today is in the field of domain adversarial training of neural networks for fault diagnostics. And if you look into the general concept of the unsupervised domain adaptation, what we typically start with, we would have a data set that is labeled for our for the starting point, and we do train a source classifier on it, and it works for us quite well. So now we have a new data set, and the data set does have some similarities with the source data set. However, if we apply the very same classifier that we trained on our source data set on the target data set, it will perform quite poorly. However, if we then try to align them and to adapt the model that we trained here to the conditions that we would have on the target data set, then our algorithm will perform much better, and in this case we can really start using that. So what it actually boils down to is that we are trying to align these different distributions and to overcome the domain gap between the source and the target domain, and to find a representation in which we can really learn it, and to learn this the representation also through deep learning algorithms. And one of the best performing algorithms in the field of domain adaptation are the adversarial networks, and they do work where their basic principles are similar as in the case of generative adversarial neural networks. However, in this case, we are applying them to compete between each other, to, on the one hand, to make the distributions as similar as possible, but on the other hand, to make the distributions as indistinguishable as possible, to be able to distinguish them as well as possible. Sorry about that. And that's the basic concept that we have. So on the one hand, we have the classifier, and this is our main network. So we train our algorithm to classify our faults well. And on the other hand, we add additionally this domain classifier, and the task of the domain classifier is to distinguish between the two domains. And what we add additionally here is this gradient reversal layer, and then we can combine the two losses and learn this as a min-max problem. And this enables us to train the algorithm in such a way that at the end, the features that we actually train here become indistinguishable for the domain classifier, but still we are achieving a good classification performance here. So that's the basic concept here. So let's take a look how we can actually apply it to the case of fault diagnostics. So let's assume we have a source data set, and on this source data set we did observe all the different faults that may be able to occur. We also had sufficient healthy conditions. And now we have a new data set, and this is our target data set. And in this case, we also did collect quite some data, but now we don't know at all where are the faults and how to classify that. So that's the basic setup. We do have all the information on the source data set available, but also on the target data set, we do assume that all the faults could actually occur. And we applied this on a small case study on the CWRU dataset, which has been used as a benchmark dataset. It has 10 different classes. It's actually 3 different faults, but with different severity levels. And then it also has 4 different loads, and the loads we were considering as our domains. So the task was now to train the algorithm on one domain and then to apply it to all the other loads. And the baseline is the case where we don't perform any domain adaptation at all. So we train our models on one domain and then purely apply it to the other domains. And as you see, the baseline is already quite high, so it's actually 95%, which means that the differences are not so big and it's already quite well transferable. However, if we now apply domain adaptation to it, we can improve the performance to 99%, which is still quite a significant improvement. So the algorithm learns to align the 2 domains between each other, and it's always pairwise transfer. So that's kind of the basic setup. And in the basic setup, we are assuming that we have on the source data set observed all the different faults. And then for the target data set, we also assume that there will be all of the different faults already available. And we also want to apply them later on also to all the different faults. However, this is not a very realistic setup, because when we start testing our algorithm, we cannot assume that we would have all the different faults already available in our data set, because we may just have, so either observe just the healthy conditions up to now, or possibly just one fault, and we would still like then to develop the model already at that phase and then to test it later on all the different fault types. Looking into who did something in that direction, so there was an approach that was proposed, and in this case on the target data set, so on the target operating conditions, we did not have all the faults available. However, it was also only possible to test it just on the faults for them on which the model was also developed. So again, this is not a very realistic setup, and the more realistic setup is the case that we do assume that on the source data set we do have all the faults available. But during the model development, we may have some faults available, but we don't know which ones they are, and also we don't know how many of them there may be there. But later, when we apply it in real application, we would like then still to be able to classify all of the faults correctly. So the very naive setup would be that we apply the very same what we actually did. So we just align between the source and the target domain without knowing how many faults there are and without knowing which of the faults are actually present, and then we still would like to test it here. So this is just a figure of the case where we apply this alignment to the NIST data set, which is a classification data set for different digits. And as we see, this naive alignment doesn't work for us that well, so it really gets misaligned because it does not know which of the faults actually aligned or which of the classes to align to which parts of the data. So inspired by this challenge, we're looking for a solution, and the solution that we actually came up with is that instead of trying to align these 2 different domains jointly, since we already know that the source domain does contain a good representation of all the different faults, we can actually keep this good representation in the source domain and then take the target domain and then just unilaterally align the target domain to the source domain. So this is the proposed unilateral domain adaptation approach. so that we keep what we keep a good representation that we know from the source domain, and then just align the target domain to it. So if you look how this can be implemented, so on the one hand, we still have the loss that we actually had before. So we still have the domain adaptation loss, and we still have the classification loss, and we add one additional loss that that is the consistency loss. So we pre-trained the model on the source domain, and then we add this consistency loss that actually penalizes the deviation in the feature space from the source to the target domain here. And this is the additional loss that it has added here, and it can be also regularized to decide how severe this alignment needs to be. And in order for us to test it on a known case study, we applied it to the domain adaptation task between NIST and NIST-M dataset. So the NIST dataset is just the black and white digits here, and the NIST-M dataset actually the colorful digits here. And what we did here is we started then dropping the number of classes, and then we looked into how it would perform, or how the domain adaptation would perform here. So this is where we had the full information when all the classes were available. So obviously then both of the models actually perform well. And now we start dropping the information in the target data set during the training. And it still keeps at quite a high level. However, when we start then taking away quite a lot of classes, then the performance drops dramatically. However, if you look here to this unilateral alignment, when we still keep the representation of the classes from the source domain, the performance actually keeps quite at a high level, even when there is just one class left. How is this transferable to the case that we are interested in for the fault diagnostics? We're actually trying to classify different fault classes. So we can apply it to different combinations, but the case study that I will just show you here is, so we assume that on the source data set we do have all the fault and healthy classes available. But for the target data set, at the training time, we may just have the healthy class available. And this is really quite a realistic setup, because when we have, for example, a new machine, we would still like to have a model that works well for us. However, we may not yet have observed any fault, but we would still like to use this model later on during the entire usage time. So we did apply it to the case, again, to the same CWRU data set. It's again the bearing data set, and the baseline is obviously again the same because we train the model and then we apply it to the test data set. However, now we assume that there was just a healthy class available and there was no faulty information on the target data set available during training. And now with this unilateral alignment that we proposed, we can improve the performance to 98%. So if you compare it to the performance that we had before, so there we had the 99%, but we did have information of all the different classes available already during training. So still it is quite a significant improvement, but obviously we are not coming to the same level where all the information is already available. So this was the part for the unsupervised domain adaptation, but what I also wanted to discuss with you is the case where we have, for example, a new system, a new machine that is operated, and we may not only lack the faults, but also we may not have yet collected all the different operating conditions. And we may not be able to collect them immediately because our machine may be operated, maybe have some operating regime. So we may need to wait for quite a long period of time until we would have collected all the operating conditions. So the question is, how can we actually transfer the operating conditions without any labels in our data sets? So before I start with that case, I need to introduce kind of one concept to you that we have been using, and it's maybe not in the same way that others are using this concept. So that's it's just a short introductory part because I will need it to explain the rest to you. So typically, so we are now in the context of fault detection. We now not training our, or we cannot train our classifier, and we cannot apply a classification algorithm. So we are also not trying to apply some balancing approaches or to perform unbalanced classification. What we actually would like to do is instead of even trying to learn any fault patterns, we would rather like to, or we prefer to monitor the healthy system conditions and to learn a good representation of the healthy system conditions. So the idea behind it is that we do collect all the information from condition monitoring data, and then we kind of map it to a health indicator. And this kind of mapping, I'm just explaining to you very shortly. So the basic idea is to apply, on the one hand, a feature learning step. So that's a typical autoencoder. But instead of using the autoencoder for the fault detection part, we take the features of the autoencoder and then we feed them into a one-class classifier. And that's not the typical one-class classifier where you get the output 0, 1, so is it abnormal or normal? But instead, we translate it to a distance measure or to a similarity index that measures to us the distance of the training data. So on the one hand, we train it to map to a target, and on the other hand, based on the validation data set, we set a threshold for our similarity index, so we normalize it to be 1, and then we start monitoring it afterwards and us trying to measure the distance to the training data. So that's just the basic concept. On the one hand, we are training it to map it to 1, and then we take the validation data set, which is a subset of our training data set. We set the threshold based on it, and then afterwards we start monitoring it. And obviously, when it starts deviating, or when our similarity index starts being dissimilar, that is when we start raising the alarm. And what we can actually even do more, so once we detected something here, we can go back to our autoencoder, and then we can analyze the residuals, and based on the patterns in the residuals, we can actually distinguish between the different fault types, or between the different fault causes, to narrow down what could be the possible fault type behind it. So on the one hand, we are taking the residuals, we are again using the validation data set to set for us the threshold for the residual level, and then we take the most deviating signals residuals, and these are then our candidates for the deviating signals. So again, this is really just an introduction to the concept, how we were using it for the fault detection task or for the anomaly detection task. And just a very short example of how it could work. We applied it to different systems, but that was the first system where we actually applied it to. It was a case study of the generator health monitoring. We had around 300 sensors that were monitoring this generator. We had around 1 year of data, and it was 5-minute snapshots that were taken, and the task was to detect when something would be deviating here. So we applied this concept of the similarity index. We trained the algorithm on the first part of the data. We set the threshold with the validation data set, which was sampled randomly from the training data set. And everything that you see here in orange, this is when we started actually monitoring it, and what you also see, so here the system was not operating, and what you see after it was taken back into operation, it started deviating immediately. And the interesting part was as well that we could actually distinguish between two different levels of anomalies because the distance was really deviating quite significantly. And it was around 100 days before the dedicated system was able to detect it. So this works quite well for a single system where we have sufficient healthy data. And what we also assume here is that when we trained our model to have a good representation of the healthy data, obviously we need to have data that is representative for all the different operating conditions, because otherwise when we start monitoring it, it will also detect something as dissimilar when it was just a different operating condition. And this is something that we would like to avoid in our condition monitoring or fault detection tasks. So now I'm really coming to the case study that I wanted to discuss with you. And this is the case where we have around not just one, but now 112 gas turbines. And we knew that there were 12 gas turbines that had a fault. Again, for each of these gas turbines, we had around 1 year of data, and it was again a 5-minute sampling rate. And each of them had around 24 variables, whereby this is the subset where the variables were the same for all the gas turbines. And these gas turbines were distributed around the world, so they were operated in different continents and in different countries. So since our condition where our anomaly detection approach worked quite well, we also applied it here. And we did not know when during the year actually the anomalies were happening. So let's assume we take the very first part of the data. So this is the first 1 month, and we train the model, and then we start monitoring it. And what you see here is that it starts deviating quite early on. So, it's difficult to judge, is this a fault or is this not a fault, and when did the fault really occur? Well, what we also see here when we look a bit closer is that our training data set did not contain any winter conditions, and obviously the winter conditions were detected as being abnormal in our case, which also makes sense because it is the similar operating condition. So now if we would extend the training data set to 9 months, well, now the models actually start performing quite well. But the question is, if something happened during this 9 months, we would also have learned it and we would have included it in our training data set, and we would not have detected anything. So the question is, how long does it really take for us to combine this representative data set, and when can we really start to monitor something? Because if we sell to our customer a new condition monitoring system and tell to the customer, well, we may need to wait maybe for 2 years until we can take it in operation, well, maybe then it will not be acceptable. So how can we make sure that we have a data set that is actually representative and that we can really use for monitoring, but also monitoring quite early on? Well, the solution to that is actually that normally we don't have just one system, but we may have a fleet of systems. So we could actually take possibly data from other systems that have experienced these similar operating conditions that we're interested in. But one of the challenges again here is that on the one hand, the systems are operated similarly, and we don't want to combine data that is dissimilar because then it's not representative and we are not detecting anything. But on the other hand, we want to make sure that it does get enriched and not uses the same operating conditions all over again. And we are still in the setup that we don't have any faults observed, so this is one additional challenge. So coming back to this, in the first case study, we looked into the domain adaptation part. We did assume that on the source data set, we did have some labels. So now we are going this path down. So now we are even in the case of the unsupervised transfer learning. And the challenge, and why is it so challenging, is that on the class, so if we have clear class structure as for our fault diagnostic data set, so we also have some structure in our feature space, so then it's really easier to align But now we don't have any labels, we don't have any structure in the data, so it's a bit difficult to guide the algorithm where to align and how to align. So if we were just telling it to combine the data, and we have a source and a target data set, well, in this case, the healthy and the unhealthy features maybe make it really mixed up, and we are not achieving anything. So this is where we apply some naive alignment, and then they are getting mixed up. And the idea that we proposed was that we actually would like to preserve the relationship between the single samples. So when we are learning a representative feature space where we are trying to align it there, so we would still like to impose that the distance between the samples is actually preserved. So that's the basic ideas. On the one hand, we would like to use the operating conditions from different fleets, but not to just combine them, but really to adjust them to the specific operating conditions. Since we do experience a domain shift, we would like then to preserve this interrelationship between the samples, and actually to expand our operating experience. And this is really how it can be seen. So we are kind of adding the operational experience from other unit to the unit that we're interested in, and normally it's really expanding it and adding additional operational experience so that the data set that is now used becoming more representative of how it's going to be operated in the future. And that's the basic setup. So on the one hand, we have still this domain discriminator here, and this is similar to the case where we are applying in the unsupervised domain adaptation. However, now we don't have any classification loss since we have the one class classifier, and we don't have any additional information from here. But what we actually add additionally is this multidimensional scaling loss. So this is the loss that enables us to preserve the distance between the samples in the input space and in the latent space. So that's the additional loss that we are adding. So on the one hand, we are taking two samples in the input space, and we are imposing that this distance or the representation of these samples can actually be scaled or rotated, and we add also the scaling parameter here that it's possible to have different scaling factors, but we would like them to be minimized. So that is actually the trick to be added, and surprisingly it then worked quite well. So this was the case what we had before. So this is the case where we had 2 months of training data, and when we when we then start monitoring, then again the algorithm deviates quite early on, and this is the case where we did not have the spring and the winter conditions in the training data sets available. However, now when we use the experience, so we still use the 2 months of data, however, we enhance this experience, this operating experience from other units, and when we now start operating, then it does detect the new operating conditions as being normal, and it does detect the abnormal fault actually that is happening at the end. It's really something that is really deviating, and then it's able to detect the fault. So the two setups that I showed to you, on the one hand, we were transferring from one operating condition to the other. So this was the case from the CWRU data set. On the other hand, we were transferring the healthy operating conditions from a single system to a whole fleet. And this was demonstrated on the case of completely unsupervised learning, where we did not have any labels, even in the source data set. And one additional direction that I did not present to you, but we have been working on recently, is also to transfer from synthetic data to real data, so to overcome this domain gap as well. And in the last part, if I still have some time, I would like to present to you one more concept, how to overcome this challenge of lacking generalizability, but also lacking interpretability or explainability by integrating physics into the learning process. So the basic idea is actually to use the best of the two worlds and to apply hybrid approaches. So on the one hand, still use the learning capabilities of deep learning models, and on the other hand, to add the explainability, but also the extrapolation ability of the physics-based approaches. And the basic idea is that we're actually enhancing the input space. So this is our system model that is available to us. We do calibrate the system model, and we also have the real process that we are monitoring. The process parameter measurements is what we typically would have available in real operations. And what we add on top to this is input to our models, to our deep learning models from our system models, so from our system performance models, additional the virtual sensors. And these are actually parameters that are not measured in real systems, but those that we can infer from the system models. And what we add additionally on top as an input are the calibration parameters, since they have actually shown to be quite informative of the degradation process, and are really helping us to predict the remaining useful life in this case. So this is the purely data-driven part, and then we are adding on top the virtual sensors and the calibration parameters. That's the overview of the setup. We have the physics-based system model, we have the real process, we perform the model calibration that can be performed with different approaches. So it can be a particle filter, for example, but we're also applying reinforcement learning to it. So it doesn't matter, just the quality or the performance should be comparable. Then we use the model parameters and the calibration parameters. We add additionally the virtual sensors, and we feed everything into our deep learning network, and based on that we predict the remaining useful life. And the case study that we applied it to was on a case study from turbofan engines. So those of you who are familiar with the CMAPS model and with the CMAPS data set, so this is for further development of that data set. It was so the same model was actually used, but more realistic operating conditions were used. And in this case study, we used data from 9 different turbofan engines, and 6 of them we used for training, and 3 of them we used for testing. We did have 2 different failure modes. On the one hand, the HPT degradation. On the other hand, the second fault type was the HPT and the LTP flow and efficiency degradation. Interestingly, we wanted to test it on 3 units that were actually operated quite similarly. So units 11, 14, and 15 are those that were applied for testing. And as you see, unit 14 is quite dissimilar, but even unit 15 is also dissimilar from the training data set. And we really wanted to test how does our algorithm perform in the case that the training data set is not fully representative of the testing data set. And the task that we are following here is for predicting the remaining useful life. It's a highly nonlinear process, and it is not modeled in our physical performance models, because these are the models that are just modeling the performance for us, but the degradation process is not integrated here. So this is really the learning task, and this is what we would like to infer from our models is this health index and how this health index actually progresses over time. And that's the basic framework. So we have the real process parameters here. We applied the UKF for model calibration. We informed the model calibration parameters, and we fed them in here together with with the virtual sensors and together with the observations that were applied. And we compared two different approaches. Now we're also testing one more, but on the one hand, we tested the typical feed-forward neural networks, and on the other hand, we also applied it to convolutional neural networks, also to enable it to see some past data as well. So this is what we get for the feed-forward neural networks. So on the left, you see the purely data-driven, where we don't use any additional information. These are the three units, actually. And what you see is that during the flight, there is quite some variability. If we add additionally the information from our physical performance models, it does converge quite fast to acceptable performance levels, and it also, the variability decreases also quite significantly. If we look into the performance of the convolutional neural networks, on the one hand, it does perform better than the feed-forward neural networks, but so when we add additionally physics here as additional input, as supporting information, and enhancing our input space, then again, the performance improves quite significantly. So this is also the quantification of it. So on the one hand, for the feed-forward neural network, we have an improvement between the data-driven and the hybrid for the RMSE of around 50%. We also use the scoring function that NASA was using in their competition, so it's a bit skewed, but it's still the same data that is used for it. And for the CNN, it does perform, so on the one hand, it performs better than the feed-forward neural network, but here adding additionally the physical information helps again, and the performance is improved again quite significantly. And what we may be interested in, so when is our prediction in an error bound of around 5 cycles? And how long does it have, or how long before the end of life does it really happen, and how much improvement can we really observe? So on average, we can improve this prediction horizon by more than 100%, and for some of the units it even goes up to 200%. So it's quite consistent results and quite convincing as well. Yes. What we also wanted to test is what happens if we reduce the training data set, actually. So we were using 6 units for training, but what happens if we're just using 3 units? So that's the result when we use all of the 6 units for training. We still use the same 3 for testing. And that's just a reference what you saw before. So we only tested it on the CNN because this was the better performing model. And what you see here is that actually the performance doesn't change that much. So it's plus minus 2% where it goes. So it basically stays more or less the same, although we're actually using less training data. So it does look like that it did generalize quite well, and it does require less training data. How does it help us to add this additional physical information? So on the one hand, we did see that the performance was improved, but on the other hand, we were able to reduce the amount of training data that were required, and we also were able to generalize actually quite well without using so much training data. We could improve the transferability of the model, but also improve the interpretability, because we also have this physical model and can really pinpoint how does it relate to it. And with this, I would like first to thank the particular contributors to the case study that I was showing. So the first case study was particularly performed by Jin Wang, who is a PhD student in my team. The unsupervised transfer learning was performed by Dr. Gabriel Michaud, who is a postdoc. The hybrid domain, the hybrid approaches is a PhD topic of Mana Arias, and this was in collaboration with Chetan Kulkarni and Kai Goebel, who are supporting us particularly with the CMAPS model. So I would like to thank to my whole team, but also to the collaboration partners and to the funding agencies. And I'm open to any additional questions that you may have, but also to discussion points that may come up.
Well, thank you, Professor Olga Fink, for that very nice presentation. So I would like to ask to the audience, if you have any question, please just raise the hand. We could start with Professor Tito Tinga. Yes, Professor?
Hi, Olga. Thanks a lot for the interesting presentation. I have one question on your final part of the presentation. So combining the data-driven and physical models. What you showed for the gas turbine case is that you have this system model, which is modeling the system performance. So not the degradation, but the performance of the engine. I'm trying to understand why such a model would improve the performance of your data-driven models, because the degradation itself is in your test data, in the experimental data, but the rate of degradation is not included in your system models, I think. That's only telling you if there's so much degradation, then this is the performance of the engine. So why would that help you to improve the performance of the data-driven models?
Well, it's actually we'll go back to the concept here. So a lot of information on the degradation is actually included in the calibration parameters, because when the calibration parameters are actually starting to deviate from from the initial part, this is also telling us that the model is starting to degrade. And we are using this as an input to our model, also to learn and to map. So which levels or which calibration parameters are actually mapping to which RUL. So the model actually learns from the system state that is also represented partly by the calibration parameters on where it is on the RUL, so on the degradation parameters.
So this set of calibration parameters or calibration curves, that is what you do on beforehand. So you simulate a lot of degraded conditions of the engine, which then gives you the calibration curves, and then you use that in combination with the real degradation data.
So on the one hand, we do calibrate the model before we're using it, and then so when we're using it, we do feed it in. So we do pass it to the model first, and then feed it into as input also to the deep learning model. Actually, yes.
Yeah. Okay.
So it learns on how the system behaves over time and how to map this to the health conditions.
Yeah. Clear. Yeah. Okay. Thanks.
Is there any other question? Nope. Well, I have a very small question out of curiosity regarding the gas turbines. Yes. Could you please tell us what kind of data we're using? What type of variables were you monitoring in these systems?
So these were mainly temperature and pressure, actually. So going particularly back, possibly it was you particularly are probably referring. Just a second. So, for example, if we go to this case study where we had just a second, the 112 gas turbines, we had here just 24 variables, and these were mainly temperature pressures that were measured at different locations of the gas turbine.
Okay.
If I may, I have one other question on the first part of your presentation.
Sure.
The case study that you showed with the fleet of gas turbines, where you use the whole fleet to quickly train the model, that's something that we also typically encounter. Normally, you have to wait a long time before you collect sufficient data to be able to say something. So then I can understand that it really helps if you have a fleet of different or a fleet of similar machines, and then you combine all the information to train the models. But doesn't that give the risk that you also make the model less sensitive? Because if you look at a lot of different machines, they have slightly different behavior, different operating conditions, which then in total is accepted as normal behavior. And then I would say that for a single machine, the model then gets less sensitive than it would be if you train it just on that machine. Can you say something about that?
Sure. So maybe I need to go back to explain the concept a bit better. So, for example, when we got this data set of the 112 gas turbines, and we were given a task to detect things. So we did try, and then we used the whole data set, and then we started detecting, and it did not detect very well, actually, because, yes, as you say, because they are a bit dissimilar, and then it does not help at all. So then what we started doing is we started to look for a gas turbine that would be the most similar one, actually. So we were kind of combining pairwise. We said, yes, now we have this gas turbine. Do we have a very similar one in our fleet? And then we were only adding this one. And again, it did perform already quite well. But one of the challenges was that not all of the gas turbine had kind of a very similar one in the fleet. Because so on the one hand, we did have 112 others, but you may also end up with quite a small fleet. So you may not have the luxury to have some that is quite similar. So the concept that I was introducing now is that we're not dependent on this concept that we need to have a similar gas turbine, but we can take another gas turbine and take that experience and to align it really to the experience of that one gas turbine. So we are actually adjusting it to that one, and we are making sure that now the operating conditions become really relevant to that one. So it's kind of taking the one that did experience something that we would like to learn as well, but not to take it in the way that it was observed there, but really to adapt it to the operating conditions and to the specificities of that gas turbine. So this is the part of this transfer learning part that we're not just combining, but we are really adjusting it. And in this case, then we got for all of the turbines really also kind of cases that it was performing well, and we were able to expand our operating conditions in a meaningful way, and not just trying to look for a turbine that is similar. But it was so at the end, if we had a similar gas turbine, it was performing, of course, in the same way. But if we didn't have this similar gas turbine, then we were still lacking these operating conditions. But thanks for this question, and I'm glad that I was able to clarify things.
Yeah. Okay. Thanks. Yeah.
We have another question by Pierre.
Yes. Thank you very much, Professor Fink, for this very all-encompassing presentation of really impressive results. I have a question about the RUL. Maybe I did not, perhaps you might come back to the corresponding slide. My question is, how do you handle the uncertainty about the RUL? Is the RUL expressed as a number or as a confidence interval, and how does that come in?
Well, that's a very good question, actually, because so, in that paper that I was presenting results of, so in that one, we just were predicting one number, actually. But in the recent, so we did continue research from there, and now we also included the uncertainty quantification to it as well. It's not the most recent results, but now we're also able to add the uncertainty. And actually, what I'm showing here is not, so this is not the uncertainty. So this is just the variability during one flight envelope. So it may be a bit confusing, but so in this case, it's just one number. But in the meantime, we are providing the uncertainty as well.
Thank you. Thank you very much. And more general question, if I may.
Sure.
This may be one of the challenges, but what would you describe as the main challenges in the remaining, not the remaining useful life, but the remaining research, actually?
What do you mean? So what is there to solve? So what are the unsolved questions?
Yes, exactly. The main challenges, the main remaining challenges. Yeah.
Oh, there's still plenty of them actually. So this gives kind of an overview of the research fields that we are working on, and I don't think that all of them are still solved, or and there are still a lot of things that need to be solved. So we are still looking into the domain adaptation part, but also so for the hybrid solutions, what I was showing, there's still a lot of unsolved questions. And what we are looking in, for example, so how to add additional physical information, but also domain expertise into the learning process. And what I was showing you is kind of one way. It does require some physical models that are able to represent the system conditions well. We're trying then to explore also different ways on inducing physics into learning. Still in the fleet monitoring, what I was showing is that we were kind of using that we needed to have a pair unit. But we may also combine different information from the entire fleet, so not just from one additional unit, but from the entire fleet. So that is also something that's not yet solved. But one of the most recent research directions that we were working on is the field of prescriptive operation or prescriptive maintenance, because if we are able to predict the remaining useful life, we can actually go one step further and we can start using it in the control part, and also trying to to prolong the remaining useful life or to control it based on the information that is available to us, but also based on the relationships that we actually learn. And so there we are working a bit with reinforcement learning. Decision support I did not touch at all, because when we know what it's going to fail, when we have some uncertainty, we also still need to combine information from different assets and still need to know when to schedule the maintenance, also taking all the constraints into consideration. But these are just topics that we are working on. Of course, there are many more that are still unsolved.
Thank you very much.
But thanks for the question.
I don't think we have more time for further questions. So, well, thank you very much, Professor Olga Fink, for your presentation and for your time. And yeah, I think we finished with this colloquium. So thank you all of you for participating.
Thank you very much for attending and for the questions. I really enjoyed it. So thanks particularly to Theodor and to Piotr for the question, but also for the invitation you sent us.
Yep, it's nice, interesting. Thank you.
Have a good evening.
Thank you.
Yep.
Thanks a lot.
Bye-bye.
Thank you.